Okay, I think we are live now. All right, so we can start answering some questions. Let me just check on something really quick. I'll give actually, I guess I'll just wait a second and give people a moment to get on, which is good. I need to my bamboo. I need to open up my bamboo paper. Sorry. There it is. All right, so this is the equilibrium unit test review. And the test is on Friday. We have 3 essential skills basically, but it's not so much the essential skills, just understanding the concepts, like being able to make an ice table to find your concentrations. KSP, I think, should still have difficulty with that one, so we're gonna go over that a little bit if need be. So I'm gonna go ahead and share the paper with you guys. And I'm gonna open up for the questions. So thus far, I only have one person putting questions, and that's Ellie. Ellie, and the only reason I saw it is because it emailed me. I wanted you to put it on the Q&A app, so I'm thinking maybe you've never done that before, and that's okay. Also, your questions, 2 of them were from lecture 27, which is great. I can work with that. The other ones they look like you just took parts of sentences off the paper from the advanced planner and try to make questions out of them so that you could understand what they meant. So I'll do the best I can with that, but I don't, I'll do what I can with it. All right. So let's go ahead and let's do the ones from lecture 27 first. I'm gonna do number 10 from lecture 27 first. And what I'm gonna do is make sure I have my calculator out. Make sure that I have the workout so I can look at the number. There it is. Okay. And number 10, did it have multiple parts or was it just one question? Number 10, oh, it looks like it was kind of just one part. So use the KSP value obtained in question 9, so you have one from there, to determine if a precipitate will form when 325 milliliters of that copper nitrate is mixed with 325 milliliters of potassium carbonate. And you're seeing copper carbonate. That's why there's 2 different ones. Okay, we can do this. All right. All of a sudden, I can't find my cursor. Oh man, this is the slowest start to this. I apologize, you guys. Why can't I find the... Okay, I can do it with my mouse, but I need the pen one. This is odd. All right, I'm gonna have a slight problem. Okay, well, we'll see what I can do with this then. That is fascinating. Something seemed to happen to my... Oh, it looks like the... Oh, there it was. Okay, I'm sorry. The USB cable wasn't pushed in all the way. Lecture 27, number 10. And we went from number 9. So we're talking about copper carbonate, CuCO3, and that's our solid. Okay. And it said to use the KSP value attained from the one for number 9. So the KSP is equal to 2.3 times 10 to the negative 12th, it looks like. okay? And it gives you some molarity. So basically, though, it's giving you conditions that you don't know if it's K. You don't know if it's at equilibrium. It's giving you Q, and you're going to compare it to K. And it's going to lead, I think this might be what your other question was when you took that part of a sentence out. So we're looking for Q, and Q is going to be equal to copper 2 plus concentration times carbonate concentration, okay? Because you remember, let me just draw something here. So the equation we have, Cu, CO3, and it's an inequilibrium, that's a solid, to copper 2 plus CO3 2 minus. And this is, aqueous. And this is aqueous. Okay. So there's our equation. It would be K, but we're in a situation where we don't know what it actually is. So we have to find the concentration of copper and the concentration of CO3. And kind of going the long way with this, just to make sure we're covered, what I would do is of course, we know molarity equals moles over liter. And we know that if we multiply that, so basically, if we take moles over liter and multiply it times liters, we get the moles. I'm going way back, but I'm assuming you guys are good with that. So our concentration was, I apologize, I'm looking at the copy of a copy thing here. Should have brought the original with me. 0.50 times 10 to the negative 6th molarity, I think, which is basically moles over liters. I hope that's right. And then you multiply that by 0.325 liters. So when I plug that in, I get times 0.5 exponent negative 6. I get basically like 1.6 times 10 to the negative 7th. Okay. Oh, and this whole time I've been doing Cu. This is Cu plus, Cu2 plus. Sorry. So 1.625 times 10 to the negative 7th moles, and then you divide it by the total liters. So 325 plus 325 is 0.75, I believe. Plus 0.325. Doesn't look very good, but that's what it's supposed to be. Okay. Divided by 0.75. No, 0.65. Whoops. 0.650. And I get 2.5 times 10 to the negative 7th. Good. All right. Then that was for the Cu2 plus, and for the CO3 2 minus, I'm not going to go through that whole thing again. This is getting kind of tedious. Basically, we're doing the same thing. Is it the same? Oh my goodness, it's the exact same thing. Oh, good Lord. So you can come up with the same thing, 2.5. So that was molarity, 2.57, 2.5 times 10 to the negative 7th molarity. And because this is our equation right here, I'll highlight it in red here. Q is equal to 2.5 times 10 to the negative 7th times 2.5 times 10 to the negative 7th. So plug that into my calculator. And I get 6.25 times 10 to the negative 14th. Okay, so just a quick reminder what we're doing. We're comparing the K right here with this Q right here. And you guys remember I always put K first, K, and we're comparing it to Q. And in this situation, the K is actually quite a bit larger than the Q. Okay, what that means is that because K is reactants of our products, and actually it's the same thing for Q. Oops. No, geez, products over reactants. I'm gonna say that I'm tired. I'm just gonna throw it out there, going on a limb. All right, products over reactants. All right, so if your K is larger, that means there must be more products. Or actually another way of saying this is that if Q is smaller, then there must be more reactants than products than what it is at equilibrium. And so it's going to move to the right because it needs more products to get up to K. And the way that I write it with the K and the Q and the greater than sign facing the K, the arrow points to the right. That's another way of, that's your little hint clue. Yes, that's right. So the reaction is going to move to the right to get back to equilibrium. So if it is going to be producing product, okay, that means that, or if the system is in such a place that it's so much smaller than K, that means it hasn't reached K yet. So it won't be forming a product. I mean, it won't be forming a reactant, which means it's not going to be forming the precipitate. No precipitate. No precipitate. Okay? Because it is moving towards the products, and the products, if you remember from up here, are the aqueous ions, and so that's not the precipitate side, not the solid side. So no precipitation there for number 10. Okay? So I think that was a pretty straightforward one. And we got through it eventually. It took me a little bit longer than it should have. But that's okay. All right, so the next one that was on the list was lecture number 12. There's still nobody in here. We've been going for about 16 minutes. So I'm just gonna quick go into Schoology and say, hey guys, we're having right now. I'm kind of wondering if people realize that. And as I've mentioned before, for these, I don't really mind that much because it's recorded and people can watch it later. I just, and of course my Schoology is moving really slow, but I wanted to make sure that people have an opportunity to be in here and be asking things or whatever. So, and I didn't know if everybody was having problems, so this is probably for me too to double check. So, it doesn't look like I'm getting any messages from anybody saying, Mr. Warner, I can't get in, I don't see anything. So Google Hangout is live. Okay, just gonna post it. People, if you build it, they will come. All right, lecture 27, number 12. All right. And on number 12, it says, if a 0.50 molar solution of KOH is slowly poured into a beaker containing 0.35 molar magnesium nitrate and 0.32 molar calcium nitrate at 25 degrees Celsius, what will be the first precipitate that forms? The KSP for calcium hydroxide is 6.5 times 10 to the negative 6th, and KSP for magnesium hydroxide is 6.3 times 10 to the negative 10th. Ooh, I have my opinion already, but I don't know if it's going to be true. So let's just write down some of the information besides what problem we're in. Lecture 27, number 12. So the two substances we're comparing, so calcium hydroxide, and its KSP is equal to 6.5 times 10 to the negative 6th And then the other one is magnesium hydroxide. And its KSP is 6.3 times 10 to the negative 10th, it looks like. Okay. And the question is, which is going to precipitate first? So this is interesting to me because if you look at these, that the calcium hydroxide is more soluble than the magnesium hydroxide by a rather substantial amount, fourfold difference. What is that, like 10,000 difference, 10,000-fold difference between those two with 4 zeros? And so the magnesium hydroxide is going to precipitate quite a bit sooner if all conditions were the same. Well, they're not exactly the same, but they're not that far apart. So I would be surprised. I mean, my guess, my prediction is that magnesium hydroxide precipitates first, but we'll see. So we have, and the conditions are 0.35 molar magnesium nitrate, 0.35 molar magnesium nitrate, and what did it say? 0.032 calcium nitrate. So 0.032 molar calcium nitrate. Now, so looking at this, we're going to be dealing with a common ion problem. Here's the magnesium, right? There's the calcium. And to that, you are going to be adding 0.5 molar KOH. Okay, so you're going to be adding it in, and you're looking for which one's going to precipitate first, magnesium hydroxide or calcium hydroxide. All right, and because you're basically doing two problems is the only other piece here. So for the calcium hydroxide, I'm not going to write the whole thing since I did so much in the last question. I think you guys are getting the general idea. Your K is equal to the constant. Oh, I do need to do something as I'm thinking about it. I'm sorry, let me go back for just a second. So let's just do calcium hydroxide first. That's a solid, precipitates into calcium 2 plus, that's aqueous, plus, and there's 2 hydroxides. And if we're talking about our ice table here, all the salts go away. You start with 0 initially. Your change is plus S. This is plus 2S. So at equilibrium it's plus S and plus 2S. And so your equation, KSP, is equal to the concentration of Ca2 plus times the concentration of OH minus squared, because the 2, that is the coefficient, becomes the exponent. So the other way of looking at that is that it's S times 2S squared. So K is equal to 4S cubed. Okay. Now, that's how you do it normally. The difference is that we're dealing with a common ion. The common ion is the 0.5 molar potassium hydroxide. This 0 becomes 0.50. So now it's 0.50 plus 2S. Okay. And here, if it does not that, it's S times 0.50 plus 2S squared. And in a situation like this, you look at the K, 6.5 times 10 to the negative 6th. If it's less than 1 times 10 to the negative 4th, then this additional 2S right here, this goes away. It's negligible. Okay. I'm just going to say negligible, because K is less than 1 times 10 to the negative 4th. So we'll just go with this, okay? All right, which means that it's S times 0.50 squared is equal to K. So now if I'm gonna solve this, oops. So I'm gonna have the K for, this is calcium hydroxide, right? Yes. Okay. So 6.5 times 10 to the negative 6th is equal to S times 0.50 squared. Okay. So I'm sorry, hold on a second. Oh, wait, hold on. Well, I didn't do that exactly right because I forgot. I'm sorry. The solution, I say that was the common ion. My apologies. I forgot. The other one was in there first. So it was the point, 0.032 calcium nitrate was already in there. 0.032. Sorry about that. I forgot which one was in there first. All right, let's try that again. Oh, and then and it wasn't the hydroxide. Oh my gosh. That's okay. I got this. Right, because I said I forgot which one was in there first. So it was, I got this, we got this. No problem. Okay. So if this is our situation then, okay. So now the piece that is going to be different at this point as well, because we're dealing with this, we're looking for this hydroxide concentration. So we're not really looking for S. But basically, because this S is negligible, so I'm going to change my arrow here. The S here is negligible because K is less than 1 times 10 to the negative 4th. I apologize for that confusion. So, and you're looking for because you're adding potassium hydroxide, or not potassium, you're adding the potassium hydroxide. So you're adding this into something that you're in a situation in which you have the magnesium nitrate in there ahead of time. So when you add them together, you're going to be looking to see what the effect is on the hydroxide as you slowly add it in. So there is not a specific amount is the downside of this one, since there's already some in there for the calcium. So what that means is, and actually, so that means we probably didn't really need to do the ice table for this. 0.032 times the hydroxide squared. Sorry. So you're looking to see, this is not exactly a common ion. I don't know why. I'm tired. I'm so stinking tired. So you're looking at when this, what will the new value for, so once you have all this calcium 2+ in here, what will the value of hydroxide be that will make the KSP be 6.5 times 10 to the negative 6th? Okay. And so 6.5 times 10 to the negative 6th is equal to 0.032 times hydroxide squared. So basically we're gonna divide both sides by 0.032. And then you're gonna end up square rooting them. Divided by 0.032. So you're square rooting that, and you're square rooting that, and your OH minus, let me pull my calculator for this, 6.5 exponent negative 6 divided by 0.032, and that gives me 2.03125 times 10 to the negative fourth. I'm going to square root that. All right. So for this one, it's like 1.4 times 10 to the negative 2 or something like that. 1.425 times 10 to the negative 2. So that's that was the concentration of the OH minus that needed. So, so once you reach that point, which is, that's actually fairly high. But once you get to that, then you're going to have that precipitation. The other one then is the magnesium hydroxide. It's the exact same situation if we go back and look at it, because it's the same type of formula, calcium hydroxide, magnesium hydroxide. We're set up the exact same way, but over here, for where it has calcium is 0.032, we're going to put magnesium, which is 0.35. So, and that was, what was that, KSP? 6.3 times 10 to the negative 10th. 6.3 times 10 to the negative 10th is equal to 0.35 times OH minus squared. Divide both sides by 0.35. So OH minus, which is squared, is equal to 6.3 times 10 to the negative 10th divided by 0.35. I'm going to do square root on both sides. 0.3 exponent negative 10 divided by 0.35. 1.8 times 10 to the negative 9th. I'm going to square root that. All right, and I get the OH minus concentration equals 4.24. 3 times 10 to the negative 5th. Okay, so then, wow, this is a much smaller. So once, well, look at that. Look at that concentration times 10 to the negative 5th. Wow, that is substantial. That's like right here. I mean, that's basically what I was saying. When you reach a concentration of 4.24 times 10 to the negative 5th, the magnesium hydroxide will start precipitating. Once you reach 1.4 times 10 to the negative 2, then the calcium hydroxide will start precipitating. And this is calcium hydroxide. This is magnesium hydroxide. And so that means that the magnesium hydroxide concentration is smaller, so it's going to reach it first. So that means that this is the one that will be formed first, will precipitate first. And interestingly enough, that was kind of our prediction, the magnesium hydroxide, because its K was so much smaller. And the difference between the two concentrations that you started with was only tenfold. So it makes sense that the answers end up being 1,000-fold difference, but that magnesium hydroxide is clearly the one that will precipitate first. So good. Okay, done. How's the next one down? All right, the next questions were a little bit vague. I'm going to do the best I can with them. So effects on products and reactions based on stresses. So let's do this. Effects on products and reactions based on stresses. Let's do a reaction. I'm just going to make this up. I think it would be fine. if we have H2, 2H2 as a gas plus O2 as a gas is in equilibrium with 2H2O as a gas, okay? And so if we stress this system, and there's different ways we could stress it. We could say we're going to increase the H2. What will be the effect on the system? And so if we do that, then, or therefore, whatever that to be, the O2 concentration is going to go down. And the H2O concentration will go up, right? We've stressed a reactant. We've increased the amount of H2. So it's going to shift it's going to favor the products to get back to equilibrium, thinking of your teeter-totter. And if it does that, then it's going to consume some of the oxygen. Now, when you're all said and done, the amount of H2 will actually be higher. But that's only because you just added a bunch of H2 to the system. If you let's see, so that's what happens with those concentrations, and that's the effects on the products and reactants. Maybe this is a we'll say that this is an endothermic reaction. So let's say there's 50 K, you have to add to the system 50 kilojoules. Then if you increase the temperature, okay. Oh, and by the way, so for the other one, K is same. K is the same. That'll come up a lot. Okay. If you increase the temperature, then it's like you added another reactant. It's going to shift to the product side. So in that case, O2, the concentration of O2 and the concentration of H2 both go down, and the concentration of H2O goes up because it favors the product side, right? And you would say that what happens to the value of K? Well, if you increase the temperature, it was endothermic, and so it shifted to the right, made more product, and K is product of a reactant. K is going to increase. It's the only way that K is going to increase. Lastly, we'll talk about pressure, but we'll talk it in this way. Let's say we decrease volume. If we decrease volume, it just so happens that you're increasing pressure because they're inversely related. And so there's a smaller space. If you increase pressure, you decrease volume. It's a smaller space. There's less area to move. So it's going to favor the side that has fewer moles. Okay. So therefore, it's going to be just like B in that O2 and H2, their concentrations decrease, and the concentration of H2O increases. K stays the same. It only changes with temperature. So, I mean, when I first started thinking of it, that's what I was thinking of when I wrote that. But I'm not sure exactly what the question is attached to that one. So hopefully that helps. And Ellie, I hope that we're making progress there. Another question that I had was effects on Q and K of reaction given stresses on the system. Oh, well, I mean, I guess really that's what we've been doing. That was kind of like number 12, where you had to find the Q of each of them and compare it to the K, whatever point you reached at to get to equilibrium. So whereas you keep adding, Q is everything but equilibrium. No, I'm sorry, Q is everything. Every now and then it equals equilibrium, but that's only one case. So Q just when you don't know if you're at equilibrium or not. Actually, number 10 is a great example of that too. But let's just go look at these ones right here. So in this situation, K, this is how it's being affected. Well, it only gets affected when there's temperature. So, and that would be the same thing for Q. It's just a matter of figuring if it's at that place. in the system. So when I say number 10 is a great example of that, if we go back. Okay, here. So in this situation, you were given concentrations of two solutions that were put together. And because it didn't tell you if it was at equilibrium or not, you had to treat it as Q. So once you found Q, then you compared it to K to see where you were and what was going to happen to that system. And so number 10 is a great, I guess, a great example of this, because it turned out that Q was much less than K. And so that meant that the products were higher in K. It had to go to the product side to get closer to K. And the way we wrote it, it indicated it. But excuse me, that makes a little bit more sense, I'm hoping. So just remember that the only way to change K, to actually change K, is with temperature change. If you're wanting to know if a system is going to move, which way it's going to move, you solve for the Q, you compare it to the K, and then you can just decide if Q is less than K, then it's going to move towards the products, and if Q is greater than K, it's going to move towards the reactants. So, all right, so that answers that one. Sabrina, I see you have a question. We have not gone over number 1 on the practice test. Unfortunately, I don't know if you mean the multiple choice or the free response. I'm going to assume that you actually mean the free response. So, so I'm going to go ahead and look at that one. So it says a 350 milliliter saturated solution of magnesium hydroxide is prepared at 25 degrees Celsius. The solubility product, the KSP, is 1.8 times 10 to the negative 11th, I think. Let's try a new paper here. Okay. So practice test. Oh, I see. Sabrina, you said multiple choice. Got it. Okay. So this is multiple choice number 1. All right. So actually, let me go back up to the top. Okay. So what is the molar solubility of silver chromate? So we're looking for molar solubility, which is S. So we're looking for S. And we're doing that for silver chromate. So it's silver 2 chromate CrO4. And that's a solid. It dissolves into its 2 ions, Ag plus, aqueous plus, oh, and there's 2 of them, by the way. CrO4, 2 minus, aqueous. Okay. So we have our ice table, and we don't consider solids at all. Initially it's 0. That's not a common ion problem. It just wants to know just what is molar solubility for this substance. So this is going to be a 2s change on this side, and this is just a 1s change. So at the end it's 2s, 1s, and your K, Sp, is equal to Ag plus squared, concentration of Ag plus squared, times, because 2 is the coefficient, times CrO4 2 minus. So then the KSP is 8, what did I say, 8 times 10 to the negative, and that's 12. 8 times 10 to the negative 12 is equal to, and we said that the Ag plus is 2s, so that's 2s squared times the CrO4 2 minus, which is just s, which is equal to 4s cubed. So 8 times 10 to the negative 12th is equal to 4s cubed. Divide both sides by 4. You're left with 2 times 10 to the negative 12th is equal to s cubed. So we're going to cube root both sides, which is the same as I'm looking at it as the options. We're looking at the options. So s is equal to 2 times 10 to the negative 12th to the 1/3. It's the same thing as writing that cube root. So that's your answer. Don't forget that when you're looking at this, if that's your coefficient, it becomes, because you're doubling the concentration, right? The S, which is the molar solubility, the S is the CrO4 minus. Well, when it dissociates, if you have 10 of these, you get 10 CrO4s, but you get 20 silvers. So that's why it's 2S, because it's double the concentration of CrO4. So then you're just plugging that in, but you have to square it, because if we're calculating K, we've said that the coefficients become the exponents. So that's why it becomes 4S cubed. So that's how you get the answer number 1. All right. All right, so good deal. Sammy Cho, can you explain number 4 on the Ice Baby worksheet and number 4 on the practice test multiple choice? Yes, so we're already on the multiple choice. So I'm just gonna go ahead and go to the multiple choice number 4. And that is, what is the number of moles of CSO? Because it's a whole big problem. Okay. I've done this a few times now, which is okay. I just hadn't anticipated it'd be that much, that many questions on this. So CS2 is in equilibrium with CH4 plus 2H2S. Now, these are all gases too, which I don't think it has a bearing on this question. Might have another question. And so if we have our ice table, and it's all in 2.0 liters, right? So however many moles, you're just going to divide by 2. So for H2 is 4.00 divided by 2, so 2.00. And now it's in molarity, by the way, because we're doing this ice table. It's 2.00 there. For the CS2, it was 2 moles, so divided by 2 liters is 1.00. The CH4 was at 0.5 divided by 2, which is 0.25. And the H2S was at 2 moles, so that was also at 1.00 molarity. And then it says that at equilibrium, the CH4 is 0.50, which means that you had to add 0.25. So that means you moved, it was product favored the reaction. You produced 0.25 more molarity of that concentration of CH4. And stoichiometrically, that means that everything's going to be based off the 0.25. You're just going to multiply times the coefficients. So 0.25 this is a change of 0.50. So our answer is 1.50. That was adding it to the product side. That means it's being subtracted from the reactant side. Minus 0.25 gives us 0.75 for the CS2. And for the H2, 0.25 times 4 is 1. So minus 1.00 gives us at equilibrium, positive 1.00. So now let me just go back and double check. We're looking at number 4. What is the change in the number of moles of H2S present as the system moves from its original state to the equilibrium described? So we're looking at H2S, and it wants to know the change in the number of moles. So I had 0.50, which would be D. Oops, it all shifted down. Oh, did I forget to remove, what the? It's the third choice, so that should be C. Uh-oh. If my key might look different. Wow, something's wrong with my key. Anyways, because there's no choice on A, so it should all shift down. So that's ABC. So 0.50. Good. All right. Now, number 4 on the Ice Baby table, or I'm sorry, questions. So number 4 on the Ice Baby. Okay, let me see if I can find that one. There it is. Okay. Oops, except for that's not the question. That won't work. Do I have that worksheet? I might not. Oh, I do. I'm sorry, just give me a moment. I have to go to Schoology. Equilibrium. Oh, the question is, did I actually load the ice? Oh, I dislike it when I fake myself out. I don't think I actually loaded the original. It's difficult to do the problem if you don't know what it says. Okay. Let me take a look at something. Okay, this will take me just a second, unfortunately. Okay, so I have to, I thought I had a copy of the test here at my house and I don't. So I have to open up my Citrix connection and take a look at it through that to see the document, and then I'll be able to do number 4. All right. My apologies for the length of time this is taking. It's burning a lot of time, especially if you're at home watching it. Again, my apologies. Okay. All right. So number 4 says, consider the reaction, the CO2 plus H2 yields H2O plus CO. And wow, this is being set up very similarly. I guess I can see why you asked it. They're the same style question. Okay. So, all right, let's try this again. You had, for number 4, it was CO2 as a gas plus H2 as a gas is in equilibrium with H2O as a gas plus CO as a gas, and it is balanced. And so it gives you the things at the initial. The H2 is at 0.2 molar, 0.20 molar. The CO2 is at 0.30 molar. The H2O and CO are both at 0.55. Okay, so that's the initial. And when the system is cooled to a lower temperature, 30% of the CO is converted back to CO2. Calculate the Kc. Okay, so 30% of the CO is converted back. So here's the CO, that's the 0.55. So that change is, we're losing negative 0.55 times 0.30. Okay, so 0.55 times 0.3. And I get 0.165. So that means we're minus 0.165. So if that's the amount being subtracted from that side, that's the amount being added to the other side, 0.165. 0.165. I think that's what I'm doing here. And so you get those new values. So this one is 0.465. So that's the equilibrium concentration. The next one is 0.365, right, for the H2. 0.55, I can't do this part in my head. 0.55 minus 0.165. And this is 0.385 for both of these. All right, now you're going to plug them in with products of reactions. K is equal to concentration of H2O at equilibrium times the concentration of CO at equilibrium divided by the concentration of CO2 at equilibrium times concentration of H2 at equilibrium. So 0.385 times 0.385 divided by 0.465 and also divided by 0.365. Okay. So I'm going to plug these into my calculator. 0.385 times 0.385 divided by 0.465 and also divided by 0.365. And for an answer, I get 0.8733. With sig figs, oh, it's a 2 sig fig, so 0.87. So KC, or actually KP, actually, no, it's KC because it's all molarity, sorry. There's your answer. To number 4 on the Ice Ice Baby worksheet. All right, so we've done the practice test a little bit in the Ice Ice Baby lecture 27. I've answered a couple more conceptual questions. And I'm looking over here, we don't have any more questions at the moment. Doesn't mean that you guys don't have any questions, just there's none up there right now. So it's almost 9 o'clock, and I like to keep these to an hour if I can. Please come in and ask me questions later. I'll be at school. Hopefully looking at these will get your mind jogging. I apologize on that one on lecture 27 where I went down the wrong path. That wasn't a common ion necessarily. So, but you do start off with the concentration in the ice table before you do it. You just have to know which one we're actually working with. Yeah, I'm at school really early too, so that's another good time to come talk to me. All right, guys, thanks a lot, and make sure you get some rest tonight. Good night.